This is the recording for the final practice test. And first there's a disclaimer here, so please read through this here. So you've already seen all or most of these computer problems and most multiple choice, multiple answer, fill in the blank matching questions that are posted in both the practice final test and the proctor final exam. They're taken from the previous test exams. However, there may be a few multiple choice, multiple answer, fill in the blank matching questions that are new. This disclaimer here about the computer problems, I will return to it towards the end of this recording. All right, so let's get started here. Practice final test. So here it is. Has about 35 multiple choice questions and then 10 computer problems. Again, you will hear later that I'm not going to cover the computer problems in this recording because they're already covered in the recordings that's already on YouTube for these particular problems. Okay, so let's go ahead. First three problems are about these problems here, 1, 2, and 3. First three problems are from Unit 7. That's fresh on your mind. So I'm going to do the electric currents right here. So current through a 5 ohm resistor connected to 120 volts power supply. What is the current? So Ohm's law, 120 volts divided by 5 ohms is 24 amps. There it is, correct answer. By the way, in any one of these multiple choice or matching questions, so on, these answers could be scrambled. So look for the correct answer. Do not copy down my letters here, as again, this here could be possibly scrambled for any one of them. All right, 10 ohm resistor has a 6 amp current in it. What is the voltage across the resistor? So 10 ohms times 6 amps is 60 volts. Well, again, Ohm's law. Ohm's law for a third time, 20 volt battery connected to a resistor, current is 2 amps, what's the resistor's value? 20 volts divided by 2 amps is 10 ohms. All right, next one here. So this is about parallel and series circuits. So let's see, when 4 identical 20 ohm resistors are connected in series, the combined resistance is obviously, as they're in series, you simply add them. So 20 plus 20 plus 20 plus 20, 4 times 20 is 80 ohms. 4 identical 80 ohm resistors are connected in parallel. Their combined resistance is, so in parallel, you have to add the reciprocals, 1 over 80 plus 1 over 80 plus 1 over 80 plus 1 over 80. When you all do that, you come up with a very, very small number. You invert that again, and you come up with 20 ohms. So the first answer is correct. This one here is just to remind you that in a parallel circuit, the combined equivalent resistance is less than the smallest one. In this case, in fact, they're all identical. So, and you might see that there's a shortcut. You can actually divide 80 ohms by 4 in order to get that, but that's only because they're identical. When they're not identical, like in this one here, you definitely have to do the reciprocal calculation. So 1 over 540 plus 1 over 720 equals, you get something on your calculator. It's quite small, 0.00 something, maybe 0.0 something, and then you invert that again, and then you're going to come up with 310 ohms. In fact, again, for the first estimate, it has to be less than 540, smaller than the smallest one, smallest individual one. All right, this one here covers the power law. So power equals voltage times current, as well as Ohm's law, which is resistance equals voltage divided by current. So let's see what we get. Electric power of a lamp, 3 amps, 120 volts. 3 times 120 is 360 watts. There it is. 40 watt light bulb connected to a 120 volt source. Current in the light bulb is 120 volts. 120 volts divided by, hold on, I take that back. 40 watts divided by 120 volts, which is 0.33 amps. There it is. 0.70 amps of current through a light bulb connected to an outlet. The power consumed is, so 0.7 times 120 is 84 watts. Power dissipated in a 4 ohm resistor carrying 9 amps of current. The power for that actually takes on both equations. So I first have to figure out what the voltage is, because when you look at the power law, power equals voltage times current, and no voltage is given, but power is what's asked for. So first I have to figure out what the voltage is. I do that with Ohm's law. So 4 ohms times 9 amps is 36 watts. I'm sorry, 36 volts. 36 volts times 9 amps, that's the power law now, that's 320 watts rounded. There we go. Okay, the next one is almost identical, except this time around it's a power line instead of a resistor. So this one here has 90 amps going through it instead of 9 amps. You can figure that, well, it must be at least 10 times higher. So let's do it. First, Ohm's law. 4 times 90 is 360 watts. I keep misspeaking. 360 volts. So 360 volts times 90 amps, that's the power law then, and that is 32,000 watts. So because the current goes into the equation for Ohm's law, and then it goes again into the equation for the power law, that's why it's not just 10 times more than the previous one, but 100 times more. All right, electric heater has rated at 400 watts when used 110 volts. The safety fuse in the circuit can handle 15 amps of current. How many heaters can be safely operated in the circuit? So 110 times 15 is 1,650 watts. So up to 1,650 watts with the 15 amps, that's how much the safety fuse can handle. And you divide that by 400 watts for each heater, and therefore you can come up with up to 4 heaters can be used. All right, now the next 10 questions, I believe, are kind of from a pool from a couple of units. One of them is Unit 5, the one on liquids and gases and solids, and the other one is, and I believe I actually focus on liquids here, and the other one is from Unit 6, which is about heat and thermodynamics. So the next 10 questions are from those, is from a pool there. So you won't have the identical questions 4 to 13. So everybody gets 10 different questions here. Let's just go through the ones that I have. When water is turned on in a shower, the shower curtain moves towards the water. This has to do with the pressure of a moving fluid. When you touch a cold piece of ice, energy flows both ways, mostly from the finger to the ice, higher T to lower T, but it does flow from the ice to the finger as well, just not as much. The temperature of a metal ring increases, the hole becomes larger. There you go. And there's a couple of neat next time questions that you can look at where the author of the book is trying to explain that. And you have seen that in one of the experiments that I posted as a video. Sketch shows a reservoir that supplies water to a farm. It is made of wood and reinforced metal hoops. Why is it elevated? Why are the hoops close together near the bottom of part of the tank? Higher hydrostatic pressure for both of them. Submerging glass with trapped air. That trapped air has a pressure that is more than atmospheric pressure. Any diver who has been in a bell that is lowered down can tell you that the pressure does increase. The water pressure, the hydrostatic pressure, is pushing more and more water into the submerged upside down glass, and that squeezes the air that's left in here. You know, there's no vacuum here. There's air in there, and so it squeezes it, and that means that the pressure increases. The dam is thicker at the bottom than at the top, partly because water pressure is greater with increasing depth. Somebody could argue water is denser at deeper levels, but 2 answers for that. One of them is that liquids are virtually incompressible, which means if you try to squeeze them together, it's really, really tough. You hardly succeed. Now, if you were able to do that under large pressures, which you have in an ocean, then, and this one here doesn't even look like an ocean, you know, it looks towards the beach. There, yes, it does compress it just a little bit, so the density does increase, but you have to go to very deep levels, not the levels that you have here next to the dike or dam. But if you go to, even if you go miles down in the ocean, the density of water is hardly any larger than it is towards the surface. So really the correct answer is water pressure is greater with increasing depth. Blood pressure is normally greater in your feet. The word normally is in here, I believe, is because when we're lying down, well, the blood pressure doesn't have to be larger in the feet because the heart just pumps it laterally. But usually as we're sitting or as we're walking or standing, that's when, as we do most of the throughout the day, that's when the pressure, of course, is greater in the feet to pump the blood back up to the heart. Food in a refrigerator is cooled by the vaporization of the refrigerating fluid. So look that up in the book. In drinking soda or water through a straw, we make use of atmospheric pressure. That's why in drinks like that have a lid, there is an extra little hole in there. So as you suck the liquid out, you're lowering the atmospheric pressure inside the soda drink, and if there was no hole, then that lower pressure in there would not be able to push it in. So actually the sucking there is actually reducing the pressure, which means you need atmospheric pressure on top of the liquid to actually push it in, and that's what that little hole is about in a lid on a soda. Suspend a pair of ping pong balls from two strings. If you blow air between the ping pong balls, they will swing toward each other. I don't know if I have that on a video. So I think these were the last 10 questions. You might have a certain overlap here, but other than that, some of these I had, or they're in different order. All right, so the next about 20-some multiple choice, matching questions, and so on should be the same, but again, these are the answers might be scrambled. So let's see what we come up with. Hockey puck slides across the ice at constant speed. This exemplifies the law of inertia. In fact, this here should even say the constant velocity. Strange as it may seem, is just as hard to accelerate a car on the level surface on the moon as it is here on the Earth. This is because the mass of the car is independent of gravity. So when you want to accelerate it, you need traction. The traction depends on the weight of the car. So here on Earth, where our gravity is larger, there is more weight on the car, obviously. Earth pulls it down more, and therefore there is better traction, and you accelerate the car. On the moon, well, you have less weight to accelerate, but the same amount of mass, but you also have less traction because you don't have as much weight. So pushing against it is just as hard as it is here on Earth. A 10 Newton falling object encounters 10 newtons of air resistance. The net force on an object is 0 newtons. That 0 newtons does not mean that the object is at rest. What it means is that there is no net force acting on the object, therefore it does not accelerate. Sum of the force equals mass times acceleration. So acceleration is in there. Acceleration is 0. 0 acceleration means that the velocity is constant and the object is already falling, so it will fall at a constant velocity. That's what the 0 newtons and 0 acceleration mean. A person is attracted toward the center of Earth by a 500 Newton gravitational force. The Earth is attracted toward the person with a force of 500 newtons. That's Newton's third law. You have equal and opposite forces on two different objects that are interacting with each other. There are actually now more forces because the person is not falling through the ground, so there's a support force from the ground pushing up, which also is 500 newtons. If it wasn't 500 newtons, then the person would either start floating or would sink into the Earth. For example, you could argue that the person experienced a support force of 520 newtons. Well, that's when a person actually pushes down on the ground, which means the ground is now pushing up and the person starts jumping. In that case, the support force is actually larger than 500 newtons. But usually, as we walk around, as we stand, it's the same. The support force would be the same force. But that's not even part of the question. The question is actually that the Earth experiences the same amount of gravitational force. Of course, the Earth, with its much higher mass, does not care as much as the person does. All right, this should be like there should be two problems here. There's a follow-up to this one. So Arnold Strongman and Susie Small each pull very hard on opposite ends of a rope in a tug of war. The greater force is exerted by both the same, interestingly enough, and that is Newton's third law. Why does Arnold still win? Well, it makes a bigger difference to him, large acceleration. It makes a bigger difference to Susie because she has less mass, therefore she accelerates more. And that would be, of course, Newton's second law. Notice acceleration, and then here is she has less mass. And then, of course, there's the force that Arnold exerts. There's the force. He gets the same force, but he has larger mass, therefore he accelerates less. Also Newton's second law. And then actually the one who really wins the war is the one, tug of war, is the one with the better footing here. So if he was on ice, she would be actually, with better traction, she actually would be able to do it, to win. But we assume that the ground is the same for both of them. All right, so this one. Two identical spring-loaded dart guns are simultaneously fired straight downward. One fires a regular dart, the other a weighted dart. Which dart hits the ground first? Air resistance or no air resistance, the problem doesn't mention it. Air resistance or no air resistance, the regular dart will win because they are both identical, same force therefore. This one has a more massive dart, same force divided by more mass, less acceleration, less muscle velocity, it comes out slower. This one, less mass, same force, more acceleration, it comes out faster, and therefore, yeah, it will hit the ground first. Somebody could argue, well, on the way down, this one is going to encounter less air resistance. More air resistance than the other one. Yeah, you could do that, I guess, if you really were to shoot it from a skyscraper down. Eventually, this one is probably going to catch up because it has less air resistance than this one, or less deceleration due to air resistance than this one. It might actually pass it, but we're just thinking, hey, we're firing it straight down from like 5 feet up or so. By the way, turn both pistols around, shoot them upward. Obviously, this one is going to win because it has more acceleration. Turn them sideways. Obviously, this one is going to win. It's going to go further because it comes out faster. And by the way, when I mentioned shooting upwards, what I mean by this one winning is it's going to go higher because it has more acceleration. When you shoot it downward, this one is going to win because it has more acceleration due to having less mass. All right, let's see. Okay, this one is really a new question that you haven't seen before. So I put a little story here together. Pay attention to this one here. I believe in these directions here, I repeat myself 3 times when prompted with the word Newton. Insert 1, 2, or 3 for the most appropriate Newton law inside that long text field. This long text field is actually an overkill, but Blackboard doesn't allow me anything else. So therefore, only put the number in. Do not write first or second or third. Write the number 1 or 2 or 3. 1, of course, meaning law of inertia, 2 meaning that there is an acceleration and that there is a net force on the object, and therefore the velocity changes, which means it either gets faster or slower or changes direction. And 3, if we're looking at a scenario where 2 objects are interacting and one gets the same force as the other one. So look out for that. Of course, in the story here about the shipwrecked man built the nice raft and so on, in any one of these, you can argue that all 3 laws apply. Yes, they do. But in my story, I tried to put emphasis on just one particular one over the other. So let's read the story. The shipwrecked man built a nice raft with which he takes off in a current. For most of the time, he doesn't do anything, and the velocity of the raft is the same as that of the current. Okay, so velocity stays the same, he's just going along. Sounds like inertia, Newton 1. Sometimes he needs to change direction. Well, in order to change direction, you need an acceleration. You need a force to change direction. And that's what acceleration means. Change of velocity, which means slower, faster, or change direction. So Newton's second law. Or he needs to speed up or slow down. Newton's second law as well, just mentioned it. In order to do so, he pushes with the pedal against the water. And listen carefully. In order to do so, he pushes with the pedal against the water, and the water in turn pushes back on the pedal. Two objects that are interacting with each other, they exert the same force on each other. I don't mention that here, but it's implied here, and that is Newton's third law, the action-reaction principle. Two objects exert the same force on each other in opposite directions, of course. As it says here, the water in turn pushes back on the pedal. This is called paddling. It so happens that at one time you cannot avoid a boulder in the current because it suddenly appears around a bend. That boulder slows the raft to a halt. Notice the word slows the raft to a halt, meaning there is an acceleration, a deceleration, a negative acceleration, means there must be a force that the boulder exerts on the raft. Newton's second law, that force decelerates the raft. Somebody could argue, well, but there was Newton's third law. You know, you also hit the boulder. Maybe you dislodged the boulder. True. That could happen, and now we have Newton's third law. However, that's not how I worded this particular sentence. That boulder slows the raft to a halt. It's about the raft. Yes, there is a boulder, but this is really about the raft. Otherwise, I would have said, and at the same time, the boulder dislodges. Now then I would have Newton's third law. Because it happened so quickly, he isn't able to hang on to anything and is flung forward. Why? Because he doesn't have any traction on his raft, and inertia just makes him go. I mean, he keeps going with the speed that he used to have. So that one is Newton's first law, into the water. The water is very cold, and heat transfers out of his body through his skin, mostly due to, notice there's no word Newton here. This is where this disclaimer comes in. For the remaining text fields, choose one of these here that I put in parentheses. And so let's go back to the sentence here. The water is very cold, and heat transfers out of his body through his skin, mostly due to, well, convection. That would mean that air is coming out of the skin. No, that's not the reason. Radiation, well, there isn't enough time to really radiate. So it's the skin is in contact with the water, and it conducts outward. So conduction. Now both he and the raft are floating with the current. Now we're back to Newton's first law. Of course, he needs to get back to the raft, so his hands push on, again, listen carefully, so his hands push on the water, and the water in turn pushes back on his hands. Newton's third law, the action-reaction principle. Two objects interacting. This is called swimming. Of course, somebody could say, well, as the hands push on the water, the hands are accelerating the body as well. Yeah, that's true, and then it would be Newton's second law, but that's not the way I worded it. I worded it very clearly, so his hands push on the water, and the water in turn pushes back on his hands. Therefore, I'm referring to Newton's third law. All right, question 22. When a car is braked to a stop, its kinetic energy is transformed to heat. That's always the end product of energy transformation from one kind of energy to another one. Unfortunately, that's because of friction. That's why we have to resupply fuel to the car with its chemical energy, then becomes rotational energy from the engine to the wheels. That becomes kinetic energy of the car. But then, unfortunately, friction takes away that kinetic energy and displaces as noise, and especially heat and friction due to air resistance and so on. And at the end, when we're parking, all that energy is gone, but it dissipated as heat into the air, into the car, and so on, to the tires. We know that the tires at the end of a trip are pretty warm. All right, a TV set is pushed a distance of 2 meters with a force of 20 newtons, so 20 newtons times 2 meters is 40 joules. Strictly speaking, more fuel is consumed by a car, and if an air conditioner, headlights, or even the radios turn on, the statement is almost always true. I still don't get the word almost. To me, that is always true. Now, when you turn these on, you are using energy from the battery. That means you're depleting the energy that's in the battery, which means you need to recharge the battery. As you may know, I don't think I know anyone who owns a car where they plug in the battery to an outlet near the house at the end of the day. Nobody does that. So how is that battery recharged as throughout the day it's using electric energy for any one of these here, or the heater or something like that? So it is being recharged, but not with an outlet. No, it's recharged with the alternator that's in the engine. And that alternator is directly connected to the engine, and therefore it takes energy from the combustion of the fuel to recharge the battery. And the more stuff you have on, the harder the alternator is working, and the more energy it takes away from the engine itself, and so less energy is available to the car, and you need to burn more fuel in order to make up for the friction and the air resistance on the road as you're driving. So yeah, that one is always true. Again, I don't get the word almost. All right, a moving object. Some or all of the following. So it is moving. When it is moving, it has a certain amount of speed. Velocity is speed with direction. Momentum is mass times velocity. Energy, well, kinetic energy is 1/2 times mass times velocity squared. So any one of these. This here could be kinetic energy, but if I just write energy, that implies it could be kinetic energy. So all four are correct. All right, here I didn't check these here because I noticed as I was prepping this one here that I believe I'm pretty sure these are scrambled. So Newton's first law here, I'm just going to do this here. Newton's first law, of course, is inertia. Newton's second law is, there it is, force equals mass times acceleration, or acceleration equals force divided by mass. Ohm's law is resistance equals voltage divided by current. Energy, kinetic energy, potential energy, work, ideal gas law, pressure, volume, number of moles, temperature. Did I skip Newton's third law? Equal and opposite forces. Okay. Anyway, all right, question 27. I think there's a follow-up. It's two, yeah, these go together. You have seen a really similar problem before. Well, no, okay, almost really similar. It was the woman on the board of a cliff or something. So this one here is really similar to that, but the proportions are a little bit different. So 40-kilogram kid sits at the end of a 6-meter long seesaw, 1 meter to the left of the pivot. That means from here to here, that's 1 meter. And we assume that the kid really is sitting at the end. Okay, so 1 meter, that's what it says. That means of the 6-meter long seesaw, this is actually 5 meters long from the pivot to the right. As shown, he is able to balance himself in the seesaw. How far from the pivot is the seesaw's center of gravity? Well, if this total here is 6 meters, then of course the center of gravity is at 3 meters, and that, having an overhang of 1 meter here, is then 2 meters away. So there's the correct answer. So the center of gravity of the seesaw is 2 meters. So in order to determine the torque, which is what the next problem is, we need to keep that in mind. That's the 2 meters. Do not use 5 meters. Yes, there is some wood at the end of the 5 meters here, but all the wood is all the way through here. And in order to avoid a calculus problem, use the center of gravity. If you took the lab, you noticed that. That's why we had you measure the dowels with which we hung the mobile, and that's the same explanation that I used for this other problem, the woman who's standing on the plank of the cliff. And I've shown this in one of the video recordings for the homework, where I actually do that particular thing with a board and put it on a scale and show that actually that is the case. Yeah. So 2 meters. That's where center of gravity is. So the follow-up question is, well, what then is the mass? The quick way to say is, well, he sits 1 meter off, right, over here. The center of gravity of the board is 2 meters away, so it's a ratio of 1 to 2, which means the masses are a ratio of 2 to 1. So if the kid has 40 kilograms, then the board will have 20 kilograms, which is the correct answer. Looking at it in a different way would be, well, the kid is sitting 1 meter off times mass, 40 kilograms, times gravity. Let's use a rounded 10 meters per second squared. So 1 times 40 times 10 is going to give me 400 Newton meters for the torque over here. in order for it to be balanced, the entire board has to match that, of course, pulling in the opposite direction. So the board also needs to supply 400 Newton meters, and the way it can do that is a lever arm of, oops, that's not true, that's the 1 meter, where to go, 2 meters for the board, times a mass of 20 kilograms, times gravity of 10 meters per second squared, so 2 times 20 times 10 is also 400 Newton meters, and that matches the kit on the other side. All right, this one I believe is actually 3 questions together. Yes, I believe so, yep. Okay, consider a space habitat that consists of a rotating cylinder and so on. The person inside feels as if he is pushed, in quotes, to the outside, but also feels the floor supporting him. The sensations can be best explained by inertia and centripetal force. So the support force here is pushing him inward, which then is the centripetal force, which means he is going around here, right, in this rotating space station. Now, if there was a trap door right behind him, I guess he's staying there. If there was a trap door right behind him, he takes a step backwards, well, he'd be falling out. But he's not going to fall this way. He's not. He's not going to fall this way. He's not. The way he would be falling as he steps backward is he already has this kind of motion here. It was rotating this way. He takes along the last bit of velocity that he has, which down here would be straight out. So if there was a trapdoor behind him, just take a step back, fall out, and fall out means he tangentially goes off. So that's the inertia in there. All right, let's see what the follow-up question says. Everyday language, I'm just repeating myself here. Oh, in everyday language, we are using the term centrifugal force quite often. However, strictly speaking, there is no such force. If I was called, for example, if I was called an expert witness, which I have been before because of my physics knowledge, the court case, I myself would have to be really careful in using that term or even avoiding it. Because if I, as a physics instructor, use the word centrifugal force, which I totally acknowledge is a misnomer and does not exist, there is no force outward. If I use that in a court case, then the opposing attorney can say, hey, that guy doesn't have any knowledge about physics, you should dismiss him. So I have to be really careful in order to do it. So what then happens? When a car rounds a curve, what actually pushes the driver to the side? Well, the driver would like to go forward because that's the way the car was driving, but now the car is driving in a turn, but the driver still wants to go forward. So from the point of view of the inside of the turning car, the driver is actually going to the side, so to say, but really he wants to go, or she wants to go forward. So because of his own or her own inertia. Okay, yet another follow-up one. Everyday language, we're using the and so on, my expert witness, and so on. I myself will have to be really careful. If a car is in the right turn, the driver is obviously pressed against the car door because of inertia. He's not pressed outward. No, he wants to go forward, but the car is pushed inward due to the turn. It really does feel a force, but what kind of force is that? Notice that force is not outward, because if there was no door and if there was no belt, seat belt, the person would actually fall outward. In fact, he would fall forward while the car is turning right. And I think I posted a little video with a couple of women on a golf cart where they make this tight turn, and she actually does fall forward. Yeah, in this golf cart, there is no seat belt, there is no door, so you're falling forward because of your inertia. But in a car, there is a door, and that door actually pushes you inward, so you are turning with the car. And that, of course, is a support force exerted by the door. All right, the broom balances at the center of gravity right here. If you were to saw the broom into 2 parts through the center of gravity and then weight each part on a scale, which part would weigh more? Well, the brush part, because it has a shorter lever arm, therefore it needs to have more mass. This one here has a longer lever arm. In fact, it's about here, where once you sawed it apart right here, the new center of mass of the broom, let's see, yeah, of this broom part, the stick part here would be about here. That's where a new one. So it has a longer lever arm. The torques are the same. Not the masses or the weights, the torques are the same. as long as it's not sawed apart. So the torque this way is the same as the torque this way, but with a shorter lever arm, this must have more mass and more weight. Okay, the amount of gravitational force that acts on the space shuttle while in orbit is almost as much as the shuttle's weight on the Earth's surface, because the space shuttle really is not that much higher up. Look it up. It's just a few hundred miles above the Earth's surface, while the Earth's surface is already 4,000 miles from the center of the Earth. And that counts, not from how far you're from the surface. It counts from where are you in relation to the center of mass of the Earth. This is essentially where you're attracted towards. You're attracted everywhere on Earth to all parts, but essentially it all amounts to how far are you away from the center of the Earth, and the space shuttle is not much further out. Bullets fired horizontally from a rifle begins to fall as soon as it leaves the barrel. Gravity takes over. In fact, gravity would like to pull it down while it's still in the barrel, but the barrel is exerting a support force upward against gravity. So inside the barrel, it's going straight, but as soon as it leaves, it will actually start falling. Now, you could claim that, well, there's some air resistance going downward, so it's not going to be totally in free fall, but gravity will take over right away. And somebody else comes along and says, but the bullet is spinning, and that might actually give it some lift. Yeah, well, now you have to really look carefully into all that aerodynamics here. But overall, as soon as the bullet leaves the rifle, the barrel, it falls. Earth satellite is elliptical orbit. The satellite travels fastest when it is nearest the Earth. So picture that elliptical orbit around Earth, with the Earth being closer to one side of the ellipse. Well, when the satellite gets closer, it's attracted towards the Earth, so it speeds up. And then when it goes around its elliptical orbit away from the Earth to the further out point, well, it's being held back by the Earth, so it's being slowed down. So therefore, at the other end, it's going to be slower there. And that is Kepler's second law, and the way I just described it is by using gravitation, which is what Kepler's laws, by the way, are based on. The orbital periods of the planets orbiting the Sun depend on the, why did I not answer this? Their periods, there we go, their distance from the Sun. Ultimately, they actually depend on the mass of the Sun, but the three are related to each other. So the period, the distance that they are from the Sun, and then the mass of the Sun itself. Let's see, question 37. This could be the last one. It is. Substance transfer heat energy by some or all of the following: conduction, convection, and radiation. By the way, the word regulation, this is the only physics book I know that has that word in it, and it's kind of a neat phenomenon. After that, here after question 37, you can see these are where the computer problems are, but you're going to have different ones than what I do. And here is my other disclaimer. I'm going to go back to this one here, and here it says, and the computer problems from the previous tests and exams produce a pool of about 30 computer problems from the previous 7 practice tests and proctored exams. You know, each one of them had like 3, 4, or 5 multiplied by 7. You come up with roughly 30 computer problems, of which 10 are chosen at random for the practice final test. So the 10 that you perhaps would see on my own practice final test would be different from the ones that you see on yours. And then the same thing will happen for the proctored exam. And that is one of the reasons why I'm not going to go over these computer problems here. The other reason is that you already have them in the videos that are posted for each of the units, so review those and review previous practice tests, because it's the same 30 computer problems. All right, and with that, I have completed this review for the practice final test.